Okay, we're going to go through a few trigonometric graph examples here. We went through the notes in class or in a separate video, and now we're going to do some examples. Before I do that, though, I just want to really quickly go through what we know about these two functions here. We're not going to do any shifting today at all. We're just going to do some transformations, which includes horizontal and vertical stretches and shrinks, and some reflections as well. So given these two functions, y equals a sine of bx or a cosine of bx, sine and cosine are very similar functions. They're considered to be sinusoidal functions. They're both periodic, meaning that we have a repeating pattern that repeats. It's the same y values that repeat for a certain number of x values. And we'll talk about what that period is in a second. The sine function, if a and b are both 1, looks like this with a period of 2 pi, meaning that we stop this cycle at 2 pi, the cycle that started at 0. So this is the cycle from 0 to 2 pi, and the period is the length of that cycle, which is 2 pi. So sine starts at the origin, will hit its maximum 1/4 of the way through the cycle, then go back through that x-axis, hit a minimum 3/4 of the way through, and then end at an x-intercept. Cosine instead starts at the maximum, and by the way, the maximum if a and b are both 1 is just 1, and the minimum is -1. And hopefully remember that that is the amplitude, the distance from the x-axis to the maximum. Cosine will start at that maximum value of 1 and will end at that maximum value of 1 after the period of 2 pi. It'll hit a minimum halfway through and hit x-intercepts 1/4 and 3/4 of the way through. So one cycle of the cosine function will look like this. And again, it has a maximum of 1 and a minimum of -1. Okay. When we split that period up, if a and b are 1, obviously we'd have pi over 2, and then 3 pi over 2, and that would be the same in the other graph. But what if a and b are not both 1? Well, then whatever that a value is ends up being a vertical stretch on the function. And so these values would be a and -a. But if a were negative, let's just write this first. The absolute value of a is the amplitude. If a is negative, then we have a vertical reflection, or we reflect in or over the x-axis. So that would end up looking like this. Basically, your minimums become your maximums, and vice versa. The midline or the x-intercepts stay the same. Cosine, if we have these ideas are true for both of these functions, so I'm going to slide this over right to the middle. These ideas are true for both functions. Cosine, if we had a -a value, again, minimums become maximums and vice versa, but those x-intercepts stay the same. So this is what it would look like if a were negative. We would start at the minimum and end at the minimum within that cycle. Well, if b is not 1, then our period is not 2 pi. Our period would be whatever 2 pi divided by the absolute value of b is. This period would be 2 pi over the absolute value of b. I'm going to write that down here as well. 2 pi over the absolute value of b is the period, which would make halfway just pi over the absolute value of b. And then we could get more detailed and say that this is pi over 2 times the absolute value, but we'll get to that when we get to an example here. So b will affect the function horizontally. If b is bigger than 1, it is actually a horizontal shrink, and if b is less than 1, it is a horizontal stretch. If b is negative, it would reflect it over the y-axis, but we aren't going to deal with that in Algebra 2. So let's actually look at a couple of examples where we have a and b values other than 1. So the first one here is y equals 2 times the sine of x. What I'd like you to notice first is that b is 1. There's no b there, so b is 1. So right away we know that the period is 2 pi, just like the parent function. Okay, if b is 1, then the period is 2 pi. A quick note here about b as well. We did not mention this in class. I'll throw this out right now. B is the number of cycles from 0 to 2 pi. So if b is 1, there's one cycle between 0 and 2 pi. I'll talk about that when b is something other than 1 as well. Okay, once we know what our period is, we're going to come out to our graph and either cut our graph into fourths or eighths, fourths at the very least. The graphs that I provided you are all split into eighths, so I'm going to call that 2 pi. That pi over 2 is right there, and that would make that 3 pi over 2. Now these are all odd multiples of pi over 4 here. And I'm not as concerned about us labeling these as the 4 major splits of the graph. In this case, they're all the quadrantal angles. I'd like us to try to keep the graph as close to being scaled as possible, meaning, you know, when you plot that 2 pi way out here, 2 pi is 6.28. So, you know, kind of think about that when you put your value of 2 over here. I think putting 2 right there might be a little bit big because, you know, that would put 2 at about right there on the x-axis, and I think that's a little big. So what I'm going to do is I'm going to put 2 on our y-axis right there. There's 1 and 2. And the reason why I want to know where 2 is because that's the a value. Since a is 2, the amplitude is 2. So we know that this is going to have a maximum value of 2. And we did this in class. This is not necessary, but if you want to, at your minimum and maximum values, just put light lines where you know the maximum, where the maximum and the minimum values are. Just to help you in graphing it a little bit quicker. Again, that's not necessary. But sorry about that. But it might make the graph go a little bit quicker as we go. So what we know is this. I'm going to do a real quick sketch, and then I'm going to do it again, a little bit more detail. But we know this is a sine graph. So it's going to start here and end there and go through the midline halfway through. So the maximum's there and the minimum's there. So those points we know are going to be there, and this thing's going to look something like that. To give us a little bit better idea of what this looks like, though, we're going to take the time to put those square root of 2 over 2 points in. Since the sine of pi over 4 is square root of 2 over 2, we take the a value and we multiply it by the square root of 2 over 2 to find out where those points are. So a in this case is obviously 2. So we have 2 square roots of 2 over 2. And that is about 1.4. All right, so we know that those points are going to be at about right there on the graph. Right there. And I'm going to again put some lines there to help me with this. To quickly put these points on the graph. And I don't really have a name for these, or I don't know if there is really a name for these. I just call them the square root of 2 over 2 points, or sometimes like the halfway points, because it's halfway between the x-intercepts and then the minimums or maximums. Oops. So at all these multiples of pi over 4, I'm on that purple line then. And we know that that's it's 1.4, but let's call it what it exactly is, and that's square root of 2. So now we have a really good idea of what this function looks like, and we can sketch that cycle. That's it. All right, we'll take a look at two more here today, where we're dealing with a and b values other than 1. In the next example, we actually have an a value, excuse me, a b value that is includes pi. So when we find our period and take 2 pi over the absolute value of pi, we just get 2 because those pi's cancel out. That's okay. We can have a period that is just a numeric value without pi in it. So when we put our value of 2 out here, just mark 2 on that x-axis right there, 1/2 and 3/2 right there. I'm going to keep that in mind when I put that 1/3. I don't really want to make 1/3 any bigger than maybe this guy. You don't have to use these lines here, but I'm gonna just use it because it's there. There's my maximum value there, 1/3. This is a cosine function, so I know it's going to start at that 1/3 and then come down to begin with. Let's talk about the. Actually, we're good to go here. We can go ahead and start plotting some of these points. Oh no, I'm sorry. The square root of 2 over 2 values would be 1/3 times the square root of 2 over 2, which is approximately square root of 2 over 6. You know what? I don't have a calculator with me right now, so what I'm going to do is just give us that old rule of thumb that it's about 70% of the way up to the amplitude. Since that is 0.707, we want to go about 70% of the way up to the amplitude. Okay, so it's a little bit past halfway, but not quite, between halfway and 3/4 way, somewhere in there. We want to put those square root of 2 over 2 points. Go right in there. Doesn't have to be perfect. So let's start graphing this guy. It's a cosine, so we know it's going to start at the maximum, and it's going to end at the maximum. Halfway through the cycle, it's going to be at its minimum, and then it hits the x-axis at those points there. And now we can put those square root of 2 over 2 points in. There. These don't have to be perfect. This one was a little low, though. And there. That's pretty good. Just a couple notes about making these graphs. When you do, again, try to make it somewhat to scale. I put the 1/3 there because 1/2 is right there, so I wanted the 1/3 to be smaller than 1/2. And then make sure that you identify these as maximum values here, and that you don't accidentally do something like, I've seen this before, where we do stuff like that. You can't do that because that is a max value there. So once the graph hits that value, it's going to start coming back down. My pen's not working great right now. All right, last one here in the video. While we're talking about sine and cosine, just some stretches and shrinks. We have y equals 3 cosine of 1/2 x. Let's do one here. I'm going to change this actually and make this -3 right there, so that we have one reflection in this first group. So this graph, normally a cosine graph, looks like this, but this graph is going to be reflected, so it's going to look like that instead. Okay, that red graph is what our graph is going to end up looking like. Let's find that period first. We've got 2 pi over 1/2, which is 2 pi times 2, so we've got 4 pi. All right, so I'm going to go all the way out to my last line there. That's 4 pi. 4 pi is about 12, so I wouldn't go crazy high. I don't think putting that 3 there is a good idea. It's a little too high. I'm going to go and put the 3 right here. Okay, it's not perfect, but a little bit more to scale. It at least shows that you're thinking about what the scale is. 2 pi, pi, and 3 pi right there. Okay, so the square root of 2 over 2 points, we've got 3 times the square root of 2 over 2. I know that the square root of 2 over 2 is 0.7, so if I multiply that by 3, we're looking at about 2.1. And that's going to be kind of hard to get on here anyways, the way that I have things marked out here. But we know that it's going to be about 70% of the way up to that 3, so I'm just going to throw it in about right there. Maybe a little low. But there's 3 square roots of 2 over 2. And negative 3 square roots of 2 over 2 there. All right. So it's negative cosine, so that means that we're starting here at the minimum, and we are going to end at the minimum in this one cycle, and halfway through it's going to hit its maximum. Okay, we're going to do a lot of problems in our application problems that are negative cosine problems, where something starts like a spring being let go, and it starts at its minimum, and then as the spring goes, is let go, it goes past its equilibrium point up to its maximum, and then comes back down again. So we'll see this type of function again. I know it's going to go through those x-intercepts there, and now we just need to put those square root of 2 over 2 points in. And finally, right in there somewhere. That's it. Okay, I know we took a lot of notes in class, a lot of definitions and ideas of periodic functions and amplitudes and periods and cycles and all that sort of stuff. These are actually very simple graphs once you understand the pattern. Find your period, scale your x-axis out accordingly, scale your y-axis out accordingly, and then if it's sine or cosine, you know where you need to start, either at the maximum or at the origin. Or if it's a negative, you're starting at the origin or the minimum if it's cosine. So as we go through, I think you're going to find that these are pretty straightforward graphs.